Hello, everyone, and thank you for joining us. My name is Kunal, and today I'll be kicking off the presentation on behalf of my team, which includes Moin and Raj, for our final project in AAI 501. Now, we have chosen to tackle a highly complex and impactful challenge in the final sector. Our project is titled as a multi-stage framework for assessment. Now, over the next 20 to 30 minutes, we are going to walk you through an end-to-end machine learning pipeline. We'll also show you how we took raw, messy financial data and transform into a transparent, highly predictive engine designed to evaluate loan applications before they are approved. Now, talking about the project overview, I'll first talk about the high-level summary. To give you a brief roadmap of what we have accomplished, our framework operates in multiple stages. We started with massive lending club dataset, which initially contained over 2.2 million historical loan records and more than 150 features. To make this computationally efficient while preserving the statistical patterns, we intelligently sampled about 100,000 records. Talking about the architecture, rather than just throwing data at a classifier, we built a hybrid pipeline. First, we used an unsupervised layer, which included the k-means clustering. We did this to group borrowers into behavioral personas based on their financial health. We then took those personas and fed them into a supervised learning layer where we use three classifiers starting from logistic regression, random forest, and XGBoost. Ultimately, as we will demonstrate later, XGBoost emerged as our champion model, delivering the stronger realistic performance for predicting the loan defaulters. Now, started with the introduction part of our project. We'll talk about the business problem here. Now, why did we choose this problem? Why did we took this particular data set? Now, accurate predictions of loan default is an absolute backbone of lending institutional financial health. When borrowers fail to repay, it does not just cause direct financial loss for the bank, it forces the lenders to raise interest rates and tighten lending policies. Now, the kind of machine learning solution that we use, I'll just quickly talk about that. Traditionally, bank usually use expert based rules and simply linear statistical models to approve loans. Now, the problem that human financial behavior is incredibly complex and non-linear. A simple model cannot easily capture the nuanced interaction between a borrower's income, their existing debt, and the broader economic context. By leveraging detailed loan level data and advanced machine learning, we can model these high dimensional patterns to create risk assessment that are far more granular, adaptive, and accurate. Uh, Moving on, talking about our research objective. Now, we had basically set five goals once we took this data set. Now, the five out of the five goals, the first one was to conduct a rigorous exploratory data analysis to truly understand the distribution and relationship of our borrower features. Second was to aggressively clean, pre-process, transform the raw lending club data into a mathematically sound model-ready format. Third was to perform a feature selection using random forest to isolate the variables that actually influence the defaults. Fourth was to train and evaluate multiple machine learning algorithms ranging from linear baselines to complex tree ensembles using strict evaluation metrics. And then fifth and final was to interpret our model outputs through explainable AI, because in the final sector, a model is only useful if human analysts can legally and logically explain its decisions. Moving on, talking about the data set that we had, our raw material for this project was publicly available lending club loan data set. Like mentioned previously, we had about 2.2 million records with 150 features. After cleaning of the data, we were left with about 100,000 records. Talking about the feature categories, the dataset provides an incredible depth of information, which we broke down into three main categories, which were borrower characteristics, loan characteristics, and credit history. Moving on, talking about the data pre-processing that we did, which was mainly cleaning of the data, was arguably the most critical step to ensure the integrity of our models. We handled missing numerical values by imputing medians, which projects against skewed outliers like ultra-high incomes. Categorical features were imputed using model values. We also applied one hot encoding to translate text categories into binary indicators and standardize our numerical features to ensure our logistic regression models could converge properly. Now, what we also did was we made sure that we should avoid any kind of data leakage. For our target variable, we strictly mapped fully paid to 0 and charged off to 1, while explicitly dropping ambiguous active status like in grace period. More importantly, we made a strict design choice to exclude any post-loan behavioral features like collection agencies, recovery fees, including those would create target leakage, resulting in artificially high accuracy scores that are useless in the real world. Our goal was to build a legitimate pre-organization predictive model. Moving on, we will talk about the kind of layers that we inculcated. First was the unsupervised layer, then we had a supervised layer. Now, I will be first talking about the unsupervised layer. This brings us to the first major technical innovation of our framework, latent borrower segmentation. Before we asked any algorithm to predict a default, we apply the k-means clustering method to standardize the feature space. And most important question of this is why we did it, because raw financial numbers often fail to capture the broader context of borrower's life. By clustering dimensions like annual income, debt to income ratio, and revolving utilization, we were able to discover hidden high level behavior personas. For example, separating a stable high income borrower from a speculative debt heavy borrower. What was the output of it? Using the elbow method to optimize our clusters, we assigned every single borrower a specific cluster ID. We then engineered this cluster ID into a brand new categorical feature. Passing this latent persona into our supervised learning gave our predictive model critical behavior context that they would not have been able to calculate from the raw number alone. Now, moving on, we have exploratory data analysis, which will be taken care by my colleague Moin. So I'll be handing it over to Moin now. Over to you, Moin. Thank you.
Hey, thanks, Kunal. So let me share my screen. Hope my screen is visible.
Yes.
Yeah.
Yes.
So hi everyone. So my name is Moinuddin K. So today I'll be speaking about the exploratory data analysis part. So introduction part and about the data set, everything Kunal has explained beautifully. And let's go with exploratory data analysis. So exploratory data analysis is the first step in our project where we analyze and understand the data set before applying machine learning models. So in this graph, we can see the distribution of the target variables, which is the loan status. It is evident that the data set is imbalanced as a number of fully paid loans is significantly higher compared to defaulted loans. And this means that the model may becomes biased towards predicting the majority class, so which is fully paid loans. To handle this issue, we applied a technique such as a resampling or class weighting during model training to ensure balanced learning and to improve the prediction accuracy for the minority class. So moving to the next slide, that is this figure shows the box plot of three key financial features. So loan amount, annual income, and debt to income ratio. So across different clusters generated using the k-means algorithm. So the x-axis represents the cluster ID and the y-axis shows the value of each features. So each box plot summarizes the distribution within a cluster, including the median, spread, and outliers. So from these plots, we can clearly see that each cluster has distinct financial characteristics. So some clusters shows higher income and lower debt, indicating low risk. And while others shows higher debt to income ratios, indicating higher financial risk. So this confirms that K-means successfully segmented borrowers into the meaningful financial groups, which can be used to improve risk prediction in subsequent models. So moving to next slide. So this is our correlation heat map. So this that shows the relationship between the different features in the dataset, including loan amount, annual income, debt to income ratio, interest rate, and the cluster ID. So the value ranges from -1 to +1. So +1 means strong positive correlation, and -1 means strong negative correlation, and 0 means no relationship. So the color represents the strength of correlation. So red is positive and blue is negative. So explanation about this. So loan amount and the annual income, that is 0.26. There is a moderate positive correlation between the loan amount and the income, meaning people with higher income tend to take slightly larger loan. So second is loan amount and the cluster ID, that is minus 0.83. So there is a strong negative correlation between loan amount and the cluster ID, indicating that different cluster represents significantly different loan behaviors. And third is income and the cluster ID, that is minus 0.26. A weak negative relationship shows that income varies across cluster, but not very strong, very strongly. And the fourth is DTI and the other features that ranges from minus 0.04 to minus 0.01. So debt to income ratio has very low correlation with other variable. So meaning it behaves independently. And the interest rate. So interest rate shows a weaker correlation with most features, indicating it is relatively independent. So overall, most features have low to moderate correlation, so which is good because it reduces redundancy and improve model performance. Also, the strong relationship with cluster ID confirms that the cluster has successfully captured meaningful pattern in the data. So I'll be speaking about this ROC curves and the feature selection in the same slide. I'll be explaining about that one. So this graph shows the ROC curves, which is used to evaluate the performance of classification models. So the x-axis represent the false positive rate, that is FPR, and the y-axis represent the true positive rate, that is TPR. And the diagonal dotted lines represent a random model. So any model performing above this line is better than random guessing. So we have compared three models that we can see in the figure, that is logistic regression, that is AUC is 0.63, and random forest, that AUC is 0.6, and XBoost AUC is 0.69. So among all these models, XBoost performs the best as its curves is closest to the top left corner and has the highest AUC score. Random forest perform the moderately, while the logistic regression has the lowest performance. So accuracy, coming to accuracy, so the logistic regression, that is 0.75, and a random forest it is 0.78, and XBoost is 0.79. So F1 score lower value, that is that ranges from 0.24 to 0.28, indicates the class imbalance impact. So ROC curve confirm XBoost is the best. So although the accuracy is relatively high, the F1 score are low due to class imbalance, which shows that accuracy alone is not sufficient for evaluation. So overall, the final conclusion. So overall, XBoost is selected as the best model because it provides the best balance between the positive and the false positive. So from here, I'll hand over to Raj for this for our next topic, that is feature insights. Thanks. Over to you, Raj.
Thanks, Kunal and Moen. So, hello everyone. I'll be talking about the feature insights. So, in this slide, we focus on the most important features influencing loan default prediction. One of the strongest indicators is the interest rate. Higher interest rates are typically assigned to riskier borrowers. So, we observe a direct relationship where higher rates correspond to higher default probability. Next, the debt to income ratio, or DTI. Now, this is a critical measure of financial stress. So, borrowers with higher DTI are already spending a large portion of their income on debt, which significantly increases their likelihood to default. Another parameter is the annual income. So, annual income shows an inverse relationship. Lower income borrowers tend to default more often, especially when combined with higher loan amounts. Speaking of which, loan amounts and loan term also play an important role. Larger loans and longer repayment periods increase the uncertainty of risk of repayment failure. Additionally, the credit history indicators. Now, such as the credit history indicators, such as delinquencies and revolving utilization, provide deeper insights into borrower behavior and reliability. Overall, these features align well with real world financial intuition, which increases our confidence in the model's predictions and interpretability. Okay, so now talking about the discussions and the SHAP summary that we found out. So now in this section, we interpret the performance of our models and what it means in practice. We observed that tree-based models like random forest and XGBoost outperform logistic regression. This is mainly because financial data often contains complex non-linear relationships that linear models fail to capture. For example, the interaction between income, loan amount, and DTI is not straightforward, and ensemble models are better at learning such patterns. Another key takeaway is that feature selection improved both performance and interpretability. By focusing on a smaller set of highly important features, we reduced noise and made the model easier to understand and deploy. From a practical standpoint, this is very important. Financial institutes require models that are not only accurate but also explainable for regulatory and decision making purposes. Our approach strikes that balance by combining strong predictive performance with interpretable insights using feature importance. So, overall, the results show that machine learning models, especially ensemble methods, are highly effective for large scale credit risk assessment. Now, while our model performs well, there are several limitations that should be considered. First, the dataset is specific to lending club, which means the model may not generalize perfectly to other financial institutions or different economic environments. Second, we face the issue of class imbalance, where fully paid loans significantly outnumbered defaulted loans. This can make it harder for the model to correctly identify rare default cases, even though we used techniques like SMOOT to address it. Another limitation is the lack of macroeconomic factors such as inflation, unemployment rates, or market conditions. These external variables can significantly impact borrower behavior but were not included in a model. Additionally, temporal effects were not deeply analyzed. Economic conditions change over time, and the model trained on past data may not fully capture future trends. Now, addressing these limitations in future work could further improve the robustness and real world applicability of the model. To conclude this, to conclude, this project demonstrates how machine learning can significantly improve credit risk prediction. We developed a multi-stage framework that combines borrower segmentation using k-means and supervised learning models. This approach allowed us to capture both hidden patterns and predictive relationships in the data. Among the models tested, XGBoost delivered the best performance, achieving the highest accuracy and ROC AUC, making it the most suitable model for this task. We also identified key features such as interest rate, debt to income ratio, the DTI, annual income, and loan amount as the most influential factors in determining default risk. Importantly, these features have strong financial meaning, which supports model interpretability and trust. Overall, our results show that machine learning provides a powerful and scalable solution for credit risk assessment, enabling more accurate and data-driven lending decisions. Thank you.